Hi, my name is Hannaneh Najdataei, and I'm going to present our work Pi-Lisco, Parallel and Incremental Stream-Based Point Cloud Clustering. Technology is driving change across all areas of society. The change is so big that it is called the Fourth Industrial Revolution or Industry 4.0. In Industry 4.0, sensors play a key role to collect real-time data, and together with analyzing this data, they provide the ability for all components to talk to each other. One of such sensors is LiDAR, a high-rate sensor that captures a precise 3D representation of the world. To see how the sensor works, let's focus on a single photon or particle of light. The single photon is emitted from the LiDAR, hits an object, and bounces back. By knowing the time of the flight, LiDAR computes the distance of the reflected point. A good LiDAR has several laser beams to scan the environment. The laser beams in LiDAR emit millions of photons per second at 360 degrees in order to completely see the surrounding in terms of 3D points. Such points are referred to as point cloud. You can see an example of a point cloud on the right. In a point cloud, a common approach to highlight the objects and make them recognizable is clustering. Clustering is the task of grouping nearby points. There are many approaches introduced in the literature for clustering. So, for example, if we run a good clustering algorithm on the point cloud on the right, we will get the clusters representing objects as shown on the left. Clustering LiDAR data points, however, is not a trivial task. Every 360 degrees, or what is also called a rotation, LiDAR collects thousands of points. In this situation, running a clustering algorithm and finding nearby points would require operations quadratic on number of points. This is because, considering Euclidean distance-based clustering for instance, we need to compute distances between p points of the dataset to find the ones within a threshold distance, which is called epsilon. The other challenge is how we should process different rotations. One way is to process each rotation individually and report the clustering results at the end of the rotation. In this case, if we have a report period equal to the rotation size, then rotations will be disjoint and working on each rotation individually is fine. But what if we have fine-grained report periods to report the clustering results more often? Then we will have overlapping rotations. In such scenario, processing each rotation individually might cause redundant computations for the overlapping parts. To address the first challenge of having so many data points to cluster, several approaches use a supporting data structure like a KD tree to store and organize data before performing the clustering algorithm. This is called batch processing because these approaches first collect data for the whole rotation, then sort it in a data structure, and only after that they cluster the sorted data. By doing so, the expected complexity can be improved from quadratic on P to order of P log P. To improve the performance of batch processing even more and eliminate the need for extra sorting, Lisco was proposed a few years ago. Lisco and its parallel version Pi-Lisco provide a continuous distance-based clustering by exploiting the inherent ordering of the points as they are collected by the LiDAR. This way, Lisco improves the performance of clustering to almost linear cost in P. To do that, Lisco views all points of a rotation in a 2D matrix, where rows of the matrix represent laser beams and the columns represent steps in a rotation. It then looks for the neighbors of a point using this matrix within the epsilon neighborhood bounded box. The problem with Lisco, however, is that although it provides continuous clustering, it still works on each rotation individually. This means Lisco does not prevent redundant computations in case of having overlapping rotations. So, in this paper, we advance Lisco to reuse information from previous computations and propose a parallel incremental version of Lisco based on data streaming that we call it Pi-Lisco. But before diving deeper into details of Pi-Lisco, let's have a quick overview of data streaming. In data stream processing or data streaming, queries are constructed as directed graphs of data streams and operators, which are processing units. These queries are executed by stream processing engines or SPEs. Each operator receives an unbounded sequence of data items, also known as tuples, and performs some functions on them. In general, operators are divided into two types, stateless and stateful. In a very high level, state is considered the memory of an operator. So stateless operators like filter and map do not keep any information from previous tuples and perform processing only based on the attributes of the current tuple. While stateful operators like aggregate keep information from past. But since the past data is unbounded, these operators keep information of a portion of data, or what is referred as sliding window of the most recent tuples. The performance of a streaming query can be studied by several metrics, like throughput, which is the number of tuples processed per time unit, and latency, which is the time difference between receiving a tuple and producing the corresponding results. Now let's review the main idea behind Pi-Lisco. Pi-Lisco uses a 2D matrix, just like Lisco, to store the points of a rotation as being collected. The difference is that in Pi-Lisco, the matrix is used in a circular fashion, which means that whenever the LiDAR collects a new point, it updates the old point in the corresponding place in the matrix with respect to the point's step and laser ID. By updating points in the matrix, Pi-Lisco can search in the locality of each updated point to identify the epsilon neighborhood and update the corresponding clusters while reusing unchanged information. To achieve this, we need to know which points and consequently which clusters are affected by updating a single point. For that, we use a dynamic neighborhood graph, whose vertices are LiDAR data point and edges connect epsilon neighbors. With this definition, each connected component in the graph represents one cluster. So in the example shown here, the epsilon neighbor of point P are the ones connected to it, which are points 1, 2, and 4. We also define extended neighborhood of point P, which is a set of points that are either the epsilon neighbors of P or have a chain of epsilon neighbors to P. So in this example, in addition to the epsilon neighbors of P including points 1, 2, and 4, the extended neighborhood contains point 3 as well, because point 3 is connected to point P in the graph via other points. Now let's assume that LiDAR reads an update for point P, and with this new reading, the epsilon neighbors of P should be points 4 and 6. So now we need to update the neighborhood graph, and more specifically the edges of the updated points accordingly. To update the edges in the neighborhood graph, there are three possible cases. The first case is to keep the edge that already exists. In this example, the edge between point P and 4. The second case is to add new edges which shows the epsilon neighbors of the updated point that were not neighbors before. In this example, it is the edge between point P and 6. And the third and the last case is to remove old edges, which show the epsilon neighbors of P that are no longer a neighbor. The examples of such edges are the ones between points P and 1 and between points P and 2. After applying these three cases, the graph is updated and new connected components are formed. Now, considering the definition of the extended neighborhood, when a point is updated, the clustering of two sets of points might be affected. The ones in the extended neighborhood of P before applying the update, and the ones in the extended neighborhood of P after the update. We refer to these sets as affected points. Since connected components in the neighborhood graph represent clusters, on an update of a point, Pi-Lisco searches for affected points, knowing that these are potentially the ones that may change their cluster membership. So it is not necessary to traverse the whole graph to update the clusters. Instead, it is sufficient to traverse the affected points and update their clusters. This is the main intuition behind Pi-Lisco, to cluster the points incrementally while updating them. To parallelize the process, we partition the updates related to each point among threads. The key idea is that all threads see the same sequence of updates and then distribute the work among themselves. To achieve this goal, we use a scale gate, a general purpose data structure that allows threads to have read access to all data while work is distributed among them consistently. Also, to maintain the neighborhood graph and allow concurrent updates, we customize Stinger data structure. Stinger is a generic data structure that is suitable for graph problems while enabling parallelism. You will find more details about the query and how we adapt ScaleGate and the customized Stinger in the paper. Processing LiDAR rotations is like processing data streaming sliding windows using an aggregate operator. As explained before, one way to go is to run the processing on each rotation individually. This approach in data streaming is called multi-window aggregate. In the multi-window approach, each tuple contributes to all overlapping windows. Once a window is full and the aggregation is triggered, the result of the triggered window is computed and the window itself is evicted. We can employ the original Lisco to solve the overlapping rotations using this approach. But this would require distance computations of a point for each window, which will result to redundant computations. The other implementation is single window aggregate. The single window approach maintains tuples in a window until the aggregate result is triggered. It then computes the aggregation over the window, slides the window, and removes the stale tuples. This is how Pi-Lisco works. In Pi-Lisco, when window slides, the neighborhood graph gets updated by removing the old edges and adding new ones, which means potentially there is no need to recompute the distances for the overlapping parts. To evaluate the performance of Pi-Lisco, we implement it in Java. The code is available open source. The baseline that we compare the performance of Pi-Lisco with is the original Lisco. Both approaches are implemented as an operator in a streaming query in Libre, which is a lightweight SPE. Original Lisco is implemented as a multi-window aggregate, and Pi-Lisco is implemented as a single window. We test both approaches with a real data that is collected by a car equipped with a Velodyne sensor with 64 lasers. We compare the performance of both approaches by running them on a high-end server. We also use 4 metrics to quantify the efficiency of Pi-Lisco and compare it with the one of the original Lisco. The first metric is incremental processing workload. Here, we measure the workload for different report periods in terms of the number of edges that needs to be modified in a rotation. For this experiment, we use a static epsilon, which is the distance threshold equal to 0.7 meter. For original Lisco, which is labeled in the graph as multi-window or MW, the average number of edges to be added stays constant when changing the report period. This is expected since MW does not use the information from the overlapping portions of consecutive windows. For Pi-Lisco, however, the scenario is different. By decreasing the report period, which consequently increases the overlapping parts of the window, the workload decreases. The next metric is the average processing time per tuple. As shown here, by decreasing the report period, the average processing time per tuple in MW increases, since this results in each tuple contributing to more overlapping windows. But the Pi-Lisco's per tuple processing time stays constant, since the state of overlapping windows is shared and not updated on a per window basis. As the next metric, we study the effect of the report period on the throughput while keeping latency low. As shown, since the processing time of a tuple in Pi-Lisco is independent of the report period, the throughput does not depend on the report period either. Therefore, the clustering results can be output more frequently without affecting Pi-Lisco's throughput. But this does not hold for MW, since decreasing the report period increases its per tuple processing time. The last metric is the scalability. Here we focus on how the sustainable throughput varies when increasing parallelism for different epsilon values. As shown, regardless of the report period, MW's throughput decreases while increasing epsilon. The reason is that by increasing epsilon, threads will search a larger neighborhood, which results into higher workload and lower throughput. However, Pi-Lisco's throughput is not affected by changes of the epsilon value, since Pi-Lisco utilizes the results from previous rotations. This means although increasing epsilon increases the neighborhood for Pi-Lisco as well, it does not increase the need for updating the edges. Also, regardless of the report period, Pi-Lisco's throughput increases linearly with the number of threads. The reason is that threads can efficiently parallelize the workload. To conclude the presentation, we presented Pi-Lisco, a parallel and incremental stream-based clustering approach to perform clustering on LiDAR point cloud. It utilizes the information of the past rotations whenever possible and avoids redundant computations. Pi-Lisco also allows multiple threads to synchronize and update the clusters incrementally. Thank you for watching.